All right. Hello, welcome everyone to the last day of AstrotwinColo. We are joined today by Juan Rafael, as we have for the past week. Today is we have our final session. We'll have Juan Rafael telling us a little bit about machine learning models, and at the end we'll have our closing, well, not ceremony, but just our closing words. Okay, so I'll leave you with Juan Rafael.
Thank you, Herman. Good morning, everyone. Let me just go here on full screen mode so that you can follow. Okay, well, we've reached the last day of this lecture series on astrostats, data science, and I'm very happy to be talking to you today about machine learning. So today's session is going to be not necessarily connected to X-ray astronomy, although many of the methods that I'll be mentioning today are actually starting to be massively applied to X-ray data sets. But what I want with this session is to give you an overview of what and why machine learning is starting to play a very significant role in astrophysical research. So the lecture will introduce you to a couple of models of machine learning, and it will show you some examples as to how we use those models in astronomy. So basically, I'm going to briefly give you an introduction about what machine learning is and what different types of machine learning we use. I want to introduce you to the problem of supervised learning and how a very intuitive formulation from statistics and for probability using the logistic regression results in what people like to call a neuron in neural networks. And then I will briefly introduce neural networks in general, but very briefly, because I don't have the time. And then I will talk to you about random forest and how we can use random forest for one of the things that I find most interesting about how to use machine learning in astronomy, which is anomaly detection. And all of this I'll be framing in the context for the majority of cases of time domain astronomy. We spoke yesterday about time domain astronomy and how is very important these days to measure the variability of objects, and how the variability of objects is giving us new interpretations about the most energetic explosive phenomena in the universe. So let me start with this: how we can use machine learning in astronomy. How is machine learning being currently used in astronomy? And more and more fields of astronomy are using methods of machine learning today, and that has, I would say, two main explanations. The first one is, of course, astronomy is a very data-rich field. We get massive amounts of data from today's telescopes, and that's only changing to become even more intense. So as we will see, we will have even more data-heavy facilities that will be providing with very heavy loads of data, and that motivates the use of machine learning methods for the interpretation of those data sets. And then, of course, the second part of it has to do with the fact that we now have computational tools that allow us to actually do these things. I've introduced you to a couple of those things during these lectures. You've seen things like the Mcmc sampling, and you've seen things like the nested sampling, all these sort of things. This ability to sample complex distributions and to do it using the derivatives of those distributions is what is allowing us to do machine learning in a computational feasible way, and it's the other motivation as to why machine learning is so popular these days. So a few things you can do with machine learning. Here you have, for example, an example of imaging of galaxies, and in particular gravitational lensing. So it turns out that models of machine learning can learn to distinguish between different shapes of galaxies and can do very fantastic things. For example, instead of having to, when you look at an image like this, that is a gravitational lensing image, where you have some foreground objects that are lensing background objects that look like kind of stripes here because they've been deformed by the gravitational lens. Astrophysicists usually have to employ very complex models to try to guess what the distribution of matter is in the foreground galaxies that is producing the lensing. And those models are usually analytical models that might not be solvable or take very heavy computational resources to solve. And so what people are doing is they're learning using machine learning those functions that relate the distribution of mass in the lensing objects that explain the deformation of the images in the background. And machine learning, in particular neural network models, can be used to learn those functions, and in that way being able to actually infer the distribution of mass of the lens galaxies. One other topic, of course, has to do with precision cosmology, and I will be talking about that a little bit today. People want to be able to tell what the ultimate fate of the universe is, and one of the ways to do that is by identifying distant supernova explosions. And it turns out that finding such objects in the very rich data sets that we have today is not so easy. So in order to identify and classify the light curves that change the variations in the light profile of these objects that explode in faraway galaxies is another motivation to try to have algorithms quickly recognize those patterns. And even more fundamentally, people are starting to use machine learning models to solve very complicated numerical problems in astrophysics. For example, think of the interior of a star and think of how the actual three-dimensional solution of the problem of the stellar interior is, taking into account not only gravity and radiation, but also things like convection, etc., etc. That's a very hard to solve problem in computational astrophysics. And the interesting thing is that experts in machine learning are starting to come up with formulations of machine learning that are a good replacement for complex systems of differential equations. So we're starting to learn how to solve differential equations using machine learning. So there is a broad range of applications of machine learning, and today I am going to just focus on the particular case of how machine learning, and in particular supervised machine learning, can help us in time domain astronomy. But as you see, there's a broad range of applications that make part of this whole synergy between machine learning and astronomy. So yesterday we talked a lot about time domain astronomy, and of course, as I was mentioning earlier today, the explosive events that take place in faraway galaxies are important for understanding the physics of those phenomena, for finding things that are exotic because we have never seen, but also to characterize the growth of the universe. And as it turns out, sometimes something like a supernova appears in the sky, and when that thing happens, we can study the profile of such explosions, as you can see here, to measure and to compare that with particular models of the expansion of the universe. The reason being that supernovae are actually standard candles. So there is a correlation between the time that it takes for the supernova to come down from its peak brightness to kind of its baseline brightness, and how bright the supernova is intrinsically. So if you just measure the light curve of that supernova, you will know how bright it is intrinsically, and you can use that to measure distances in the universe and compare to different cosmological models that try to predict exactly what's going on there. So measuring these light curves is interesting, but the issue is, of course, that when you're sampling the universe, when you're taking images of the universe, once every few nights, once every few months, you don't necessarily have this very nice profile of the supernova. You don't know exactly how the light curve behaves. and therefore statistical methods of machine learning become important and try to determine exactly whether this is actually a supernova, and if it is, what its intrinsic brightness is. And this is only about to get more exciting because, as I was mentioning earlier, and as I mentioned in yesterday's lecture, there is an upcoming set of observations that is going to be just remarkably huge, terabytes of data per night. And in the case of optical astronomy, LSST will be, in the Vera Rubin telescope, will be the survey that will be obtaining a regular survey, a time domain survey of the sky using an 8.4 meter telescope that is being under construction in Chile. So basically, we're going to scan the entire sky and we're going to try to find things that suddenly appear in the sky and immediately follow them up if they're interesting enough to characterize these objects and understand whether they are new types of phenomena or actually existing types of supernova that we can use to measure the universe. And we don't even have to wait for LSST to come up online. There is already preparatory surveys that do something very similar than LSST will do, but at smaller scales. And one is the Zwicky Transient Facility, which is currently exploring the northern sky using the Palomar telescope in California to do exactly this kind of science. Do regular surveys of the sky with certain typical cadences in order to spot variability of objects that could represent new phenomena or existing phenomena that you can use to characterize the cosmological models. What's interesting about this is, in fact, the ZTF, the Zwicky Transient Facility, uses a telescope that is only 1.2 meters across, and it's a pretty old telescope in Palomar Observatory in California, which gives you an idea of the amount of interesting science that you can do with relatively small telescopes. I mean, you don't necessarily need a 4 meter or 8 meter or 40 meter telescope to do this. Telescopes of about 1 meter that are properly located can do this kind of surveys of time domain and spot interesting variability patterns in the sky. So here's the issue. When you take data with telescopes, you only have few points. For example, suppose you have different types of variability profiles for different types of explosive events, so supernova type 1a, supernova type 2, etc., etc. But all you have is actually points. It's a few points that you sample from it, and sometimes those points are noisy, or those points are separate, very far away, separate in time. So it is very hard to come up with a model that actually exploits those data points to try to give you an idea of what the actual shape of the light curve is. And I forgot to add the references here, but this is a paper from this year. Kyle Boone wrote a paper where he uses a generative model of machine learning for predicting the light curve. So there are ways in which we can take using statistics in which we can take only a few points and come up with the most likely light curve shape based on those data points. And this is very similar to what we have, of course, in all the exercises we've done on model fitting, where you have to infer basically a shape of a spectrum or a shape of a light curve based on only a few points. But this is done extremely well using machine learning models when we have enough data to train our models on, and when we have the proper statistical tools to do it. So what is machine learning? Machine learning is basically the field of computer science that uses statistics to have computers learn, or have algorithms learn complex correlations between variables in a large data set. So machine learning, basically, you can think of machine learning, and when you say machine learning, people usually think of things like artificial intelligence and things like Terminator-like scenarios. But really, what machine learning is more about doing things with data, and those things we do with data, we can pretty much divide in these three different types of things. So we can either do classification, where we basically try to separate objects into different classes. For example, if you have a astronomical survey of infrared sources and you want to separate between which of those sources are stars and which of those sources are galaxies, you can do that with a classification algorithm for machine learning. You can also do regression. So when you are interested in getting a particular measurement or a particular fit for a value of a parameter, you can do that using machine learning, basically, rather than classifying into classes, predicting the value of a continuous value, for example, the mass of a black hole. When you have a set of measurements from an X-ray binary, you can do that using machine learning. And the other thing you can do that with machine learning is clustering. So sometimes instead of classifying, because you have the actual labels of the different types, stars or galaxies, you don't know what those objects are. You just have a bunch of measurements and you just want to be able to separate them into different groups, even though you don't yet know what those groups represent. You can do that using unsupervised machine learning, which basically does not have any labels for the data points that you have, and do clustering. In fact, really, the best way in which you can think of machine learning is by saying that machine learning is a very fancy way to refer about fitting models to data. What we are doing here is fitting a particular model to a set of data points. But the issue here is that instead of doing kind of a model that is based on a particular physical model, we're going to try to learn a model that is based on the data itself. We try to find the best fit to a data set by learning from the model, from the data itself. So there's three types of machine learning. We either do machine learning in a supervised way. In a supervised way is when we have a data set that we can use to learn the correlations, because we already know the sample, we already know the function for that training set. We have the function that samples the properties of the data objects into the things we want to predict, either classes or a particular continuous variable. That's called supervised learning, where we actually have labels for the data set. We can label objects as this is a galaxy, this is a star, etc., etc. We also have unsupervised learning that has to do with the clustering that I just mentioned, when you basically don't have labels, but you try to separate objects in a particular feature space in order to group them and separate them into groups that you can then try to interpret from a physical perspective. But you don't have the labels. You don't have a bunch of labels that tell you which objects correspond to which features. So in that case, you do clustering, and that's unsupervised learning. And then there's also reinforcement learning, in which the algorithm is given additional rewards for for not making mistake. And this kind of for not making mistakes. And this type of reinforcement learning is more the kind of machine learning that you think when you think of self-driving cars or artificial intelligence-like systems, where you're actually trying to teach the model not only from the data, but also giving it additional rewards for when it makes mistakes in the predictions that it makes. So let me try to introduce supervised learning to you. This is basically the only way of machine learning that I'll be talking about today. And this is how I would summarize supervised learning. So again, you have basically a training data. You are trying to learn a function between some properties or some measurements and some output quantities. For example, the classes in which you want to classify your objects, or a particular quantity, such as the mass of a black hole. And you have a training set for which you know the relationship between those observational quantities and the quantities you want to predict. So that is called your training set. And for that training set, you extract a couple of things. You extract the features, which are basically the properties that you will use for your machine learning algorithms. This is going to be your input. So for example, if you have an astronomical data set, those inputs can be the measurements you take with a telescope, the fluxes of the particular sources you're looking at, or the colors, or the spectral properties of those objects. And those features you actually extract from your training data. And then you also have the labels, right? The labels are basically what help you relate those quantities to your features to your actual quantities that you want to predict. So the labels in an exercise of classification could be, for example, this object is a galaxy, this object is a star, etc., etc. So what you do is you extract your features and you create a model, a machine learning model that is going to basically be a function of your features, right? And of certain parameters, which are the parameters of the machine learning model. And that will predict, in the case of the classification problem, it will predict your labels. So if you're going to say, you're going to tell your machine learning model, I'm going to give you an input, which is going to be data input from my measurements, and I want you to predict whether this is a galaxy, whether this is a star, whether this is a supernova remnant, etc., etc. And the way you do that, of course, is by trying to minimize an error function. So all your machine learning algorithm is some sort of function that makes this prediction by minimizing the error that it learns from the training set. So we've been talking about minimizing quantities, and this is exactly what machine learning does in this case. It minimizes an error. It minimizes its own prediction error. And the reason why it can do it is because it has a control sample. It can make a prediction and then check against the training set to see if that prediction is actually correct. And once you have an algorithm of machine learning properly trained, that means you've found the parameters of that model that minimize your error in your prediction. Then you can say that your machine learning model is trained, and then you can then that becomes a predictive model, because once your model is tuned with the parameters that minimize the error in the prediction, and that minimization was done using the training set, you can then input new data that the model has never seen, extract the features, the same type of features that you extracted for training, and throw that into your predictive model to get a posterior for your prediction. So basically you have your training model, you now trust the model because you've learned based on a huge amount of data that you've passed through the training set, and now you have a predictive model that you can use to obtain a posterior distribution for your classes, or a probability that of the quantities you want to predict, which highlights a very important aspect of machine learning, supervised machine learning, and that's the fact that you have to make sure that your training set is characteristic of the thing you're going to try to predict. So, for example, if you're going to try to predict the properties of stars in the galaxy, you don't want to be training your data set with stars that are much farther away, for example, in the Andromeda galaxy, because they'll probably have a bias, a different property, or you're unable to fully measure the properties of those stars in order to actually train an algorithm that wants to characterize the properties of the nearby star. So you want to make sure that your training set is always representative of the thing you want to model. So here's the exercise of classification in a nutshell, with some notation on what exactly we call things. So suppose that you're looking at this problem of classifying between female persons and male persons based on features such as heights and weights, and you see that each of them has a different distribution. The males in this case are blue and the females are green, and you want to try to use those features, the heights and weights, to predict. And of course, the simplest way to do that is to kind of try to make a division here with a straight line, saying anything that's above the line is a male and everything's below the line is a female. But that's actually very complicated to do, because as you see, there's a significant overlapping here. So that's why you need more complex nonlinear models of machine learning that will attempt to do this classification better. So in the world of machine learning, these properties that you're using to try to classify or to predict your quantities are called the features. This kind of line that tries to separate between classes, it's what's called a decision boundary. So what you're trying to do when you're solving a classification exercise with machine learning is to actually find that decision boundary. and that decision boundary is not necessarily a straight line as it is here. We can call it also a discriminator. And these would be, of course, the colors would be the classes with particular labels, females or males. So again, when we do supervised classification, we're trying to find a function that takes the features and predicts the classes so that the error in that prediction is minimized. And it is supervised because you pass a data set for which you already know the relationships. So you pass all the green points, for example, to train your algorithm, and you know that your green points are females, all of them, and you pass all the blue points, you know the blue points are males. And in that way, you can test the algorithm against predictions because you know the classes of each of these points in your training set. Here's how I will link what we have been learning about probability during these lectures to the core of a very popular method of machine learning, which is neural networks. And as you will see, the very basic idea of that is pretty simple. So again, here's the problem we're trying to solve. We're trying to decide as to whether a point is blue or a point is red. And we're trying to find that decision boundary. We're trying to classify between these two types of objects based on the features. And basically, that can be done in a very interesting way if you bring up the Bernoulli distribution that we introduced earlier in these lectures. If you remember, this is similar to this is actually the distribution, the probability distribution for the success of an experiment that only has a bimodal possible outcome. So it's either heads or tails, if you remember. So you remember that we basically said that in this distribution, basically we have a probability to the exponent y, and then the complement of that probability 1 minus y to the exponent of 1 minus y. And the reason why this works is that basically you're trying to guess what the probability is in this case of getting a blue point. So you're gonna write the probability of your point being blue as this quantity here, and forget about the function h here. This is just a probability p, and when your outcome is 1, when you have a blue point, then the probability will be that probability. And then if your outcome is the opposite, is the red point, then this quantity will be so if this is 1, this will survive and this part of the equation will not survive. But if this is 0, this part of the equation survives, and then you have the complement. So basically, this gives you the probability that the point will be blue. And the interesting thing here is that in order to do this classification exercise, you can think of a quantity that you can interpret as a probability, and that quantity you can get from the actual features the actual features of your problem. So you have to model this as a quantity that depends on the features and depends on the model parameters whose outputs you can interpret as a probability. So you want something that is defined for all the real numbers, because in principle these quantities can have any value, and you're going to try to interpret that as a probability. And a very useful function to do that is the logistic regression. So the logistic regression is this type of function. So basically it's a function that is defined for all real numbers, but whose output values are defined only between 0 and 1. And that means that you can interpret the logistic function as a probability. So the way in which you train your algorithm is you plug this function that is a logistic regression, because you can interpret it as a probability between 0 and 1. You can plug that function here. So that's going to represent your probability of a point being blue. And so because you have your training set, you can tune, this is just a dot product between the model parameters of your network and the actual features. So in this case, we only have 2 features. So x will be the vector of your 2 features, and w will be the weights, what we call the weights of this particular neural system. In this, you're going to try to fine-tune the values of w so that when the point is blue, you have a high probability, because you want this to represent the probability of the point being blue. So you tune these parameters so that when you have a blue point, this quantity is high, And when the point is red, you want the probability to be low. So the farther away you are from the boundary decision, the lower you'll be in your probability on this side, and the farther away you are in this side, you'll be higher in this probability. And all you need to do is to fine tune these quantities, the weights, so that your training set makes the least amount of errors possible when you pass the features and it predicts a class. So this is how the logistic regression actually becomes a classifier. So you have a number of features, right? You have defined some weights. You define a probability, right, for each of these points. So this is the probability for each of these individual points. If you want the joint probability for all of the points, it will be the product of each of those independent measurements. And you use the training set to learn the values of W that minimize the prediction error about the point being blue or red based on the labels you have on your training point, on your training set. And the way to link those to a probability is by using a logistic regression. So this will be a system that for which you will pass an x1 and x2 value, and using the logistic regression, it will predict whether that's a blue point or a red point. And that is really at the core of what neural networks do. So basically, this is the error that you're trying to minimize in machine learning when you're using a logistic regression. So basically, again, we're trying to this is the likelihood of these points. We're going to try to minimize the error or maximize the likelihood. So the same way as we did previously, we take minus the logarithm of this quantity, and this transforms into a sum. So this is the error that you try to minimize. And basically, the way you do that is by exploring a parameter space of the features whose output, basically, this is a multi-dimensional function whose independent variables are the features, and the dependent variable is the error, and that has a surface that you're going to try to explore to minimize. And that's how you try to find the minimum possible error by minimizing this quantity. But of course, you have to be able to predict. So it's not enough to just learn a model. You have to be able to predict. So in this particular plot here, you see that the points that are a little bit darker are the training set points, and the ones that are lighter are the ones that the algorithm does not see when it trains. So typically, you want to be able to not just learn data for which you already know the labels or the classifications. You want to be able to train for the case of for data points that the model has not seen. So how do you know whether you're doing the correct job? Well, you have typically 3 different data sets in which you need to separate your data in order your training your initial data set. You need to split it in 3 data sets that will help you evaluate whether you're doing the right job, and that's training, validation, and testing. So in training, you just do this, try to minimize the error, right? Try to seek what are the values of your model parameters that minimize the error in the classification. In the validation part, of course, you pass, as you train, you give the model some data points that would be kind of the light points here that the model has never seen, and you evaluate how good that model is doing with those data points. Is it making a lot of mistakes? And then you use the validation part to fine-tune your models. In this case, your model parameters of your machine learning model. In this case, the weights W. You try to fine-tune those so that you find the minimum error for the validation case as well. And once you are happy with your validation, once your model parameters of your machine learning model give you the smallest possible error, then you can pass this validated model to a testing phase where you will just really look at how the model behaves for data that it has never seen. So for example, you can say a way to evaluate whether the model is performing well is to say, okay, is it making the right prediction 99% of the time, or 90% of the time, or 85% of the time? And that basically means that you're testing the model. You're looking at how well it's doing in predicting the different classes. So that's why you always have a training and validating and a testing set. So why is it that you need to validate? You have to be very careful when you validate, because one of the things you don't want to be doing is overfitting. Overfitting is a common problem in machine learning problems. As I was saying before, you're just trying to learn a function from your training data. But if you fine-tune that function very precisely for your training set, then you will lose your ability to generalize to other data sets. In other words, basically, what you want is actually something that looks like the middle point here, when your model kind of sets a boundary that makes some mistakes but generalize better. Because if what you're doing instead is something like this, when you have a very complex model that does the exact right classification for your training set, then if you pass another data set that looks similar to this but not exactly like this one, where there might be some red crosses over here and some blue points over here, then you will be making more mistakes. So you want to make sure that your model is not so complex that you're overfitting. In other words, that you're creating a function that is very well suited for your training set, but it loses the capability to validate. So that's another reason why you do validation. You make sure, by looking at how your model is training, you make sure that you're not overfitting, that you're not going to make more and more mistakes for the validation test as you train. One possible application in astronomy of classification models is, of course, classifying objects according to their classes, to their properties. So, for example, in the case of optical astronomy, if you want to separate objects, for example, between stars and galaxies in a magnitude color diagram, for example, in this case, you can use this kind of classification methods to do it. Because as you can see here, for example, different classes occupy different regions of this parameter space given by the colors and the magnitude of these systems, or even in color plots, like in this case. And that's basically because different types of objects have different spectral properties that result in different colors. But basically, again, trying to make a linear separation between classes here or here might be the simplest approach, but it might not be the most precise approach to do that. You want to be using, in this case, a probabilistic model that takes a training set and minimizes the error of prediction before you can apply this to other objects. So classification is one of the most common reasons why astronomers use machine learning today, and that's to take some observational features like optical measurements or X-ray measurements and classify objects into different classes. So I just introduced you to the logistic regression as a classifier, and the logistic regression is basically the basic unit of a neural network. So when you all you are doing, really, as I showed in the slide before, is you're taking a set of features, right? You're doing a linear multiplication with some weights that are the models of your machine learning model, and typically you add also a bias, and then you apply a nonlinear function. What allows you to do the training is that you will apply the nonlinear function in the case of the logistic regression, and that function in the case of the classification, binary classification, is the logistic regression. So that's what you did here, right? You had a linear product between your weights and your features, and you apply the H function, that is a nonlinear function that learns the probability of objects being of different classes. So that's the central aspect of these systems. You have a linear operation between your features and your weights, and then you apply a nonlinear function that will allow you to interpret those things as probabilities, and based on the inputs you have from the features. So that's why we call these neurons, because from a very simplistic functional way, this behaves a little bit like a neuron. You have a set of inputs that you can kind of compare to your dendrites in a biological neuron. You have a nucleus of the neuron that, in this case, will be your operation between your input from the dendrites and your weights. And then you have a function that will either fire or not, depending on what the input is. So this linear function will say, okay, the probability of this being a red point is larger than of it being a blue point. So I will fire a signal. I will say, yes, this neuron is activated. And that's what typically happens also in a biological neuron with the activation of an electrical pulse along the axon. So that's why we call these things neural networks. It's not really that they are emulating the human brain or anything like that. It's just a very basic functional correlation between a mathematical model and something biological. So you can, of course, you can generalize this for the case of more than one class. So the logistic regression that I introduced before typically works for binary problems, but that doesn't mean that you cannot do classification where you're trying to classify objects into more than two classes. And the only thing you need to do is you need to define your functions a little bit differently in order for it to do the classification. You just have to make sure that the input of each of these neurons, so each of these units will be like a logistic regression, but you just want to modify your output of your model so that you make sure that when you sum over all possible classes in which you're trying to classify, they sum up to 1. And this is basically what we call the softmax formulation, and it's basically a logistic regression generalized for more than one class, for more than two classes. Now, these machine learning models based on neural networks have become, of course, very, very popular, but they are not necessarily the only way to do classification in data science. In fact, there are some situations where you can think that maybe some kind of linear or nonlinear model that it's a single function might not be the best way to separate between objects. And let me show you an example where basically the decision boundaries here are a little bit more complicated to define, because if you want to classify between these two types, which in this case is just areas of land with vegetation versus non-vegetation, these things don't look like soft, functions that you can model with a neural network. Here we need a different type of model that provides a better interpretation of those boundaries that is not necessarily a smooth nonlinear function like the logistic regression. So another model of machine learning that is widely used in astronomy and in other fields is random forests. And random forests are based on decision trees and decision trees. And what is a decision tree? Here is basically a representation of what a decision tree is. It's a model where basically your final outcome of your model is going to be based on comparisons that you make between your features. So this is basically what our brain does all the time when it tries to decide as to whether two objects belong to different classes. You have a number of you make a number of decisions based on certain comparisons that you do of a specific feature. So if you want to decide whether what you're looking at is a lemon or an orange, the way you do that, one way in which you could do that would be by measuring the dimensions of these objects and separating classes. So first you measure the width. So if it's larger than certain amount, then you can ask a second question: is its height higher than certain amount? And depending on the answers to those questions, you can classify between the two. But of course, if the answer is no, then you have a different branch of this tree that will allow you for a different classification based on the height. So this is what's called a decision tree. And if you think about it, this is basically equivalent to having a space of features, in this case, the width and the height of these fruits. And what you're trying to do is you're trying to set separations in this feature space, and you try to come up with different regions of this space by making separations that are parallel to the axis of your model, so that when you make those partitions, you end up with regions where most of the objects belong to a particular class. So you want to what you want to do is you want to find where the locations of those partitions are that maximize the chance that in a particular region, all of the objects will belong to a particular class. So basically, you want to do that in a decision tree. And what a random forest is a collection of trees. So you can do that. You can do this many times and come up with a average solution to your classification problem by averaging over different decision trees. And of course, a collection of decision trees is a forest, a random forest. So this is another very interesting way to try to classify based on a machine learning models. And what you train on here is, of course, on exactly where you have these boundaries in order to separate objects into regions that have preferentially only one class. So basically, what you have is in random forest is that you have an ensemble of independent decision trees. And the quantity you want to minimize here is the variance, the error between individual trees. So the advantage about random forests is that they are random. They are not exactly the same. So you can, if you want to solve a classification problem, for example, of this type, and you can always try to use a different set of data points each time you train. It's coming from the same like big master data set, but you can use slightly different points. And if you have more than 2 features, you can always slightly change the features you use to do that classification for a different tree. So you train a tree slightly differently each time, and at the end you average the value that you get from every tree, and you get the final answer. So random forests do that. They train independently decision trees. In each of the decision trees, the original data set is in principle the same, but you use a different subset of that main data set, and typically you also use different features in each of those trees to come up with the final answer. So you train them separately, each of these trees, and for each split you randomly select a subset of the features or the predictors, and also you typically use a different subset of the data. So in that way you come up with a final answer for your classification problem. Early on, I was telling you about the importance for finding anomalies. Anomaly detection is basically one of the most interesting kind of fields in data science, in astronomy these days. How do you, if you're looking for a particular light curve that looks very different from the majority of the light curves, how do you spot that anomaly in a data set that has 10 billion objects? Well, anomaly detection methods in machine learning are an excellent way to do exactly this. And random forests and decision trees are a very natural way to think about anomaly detection. And you see here why. When you're trying to separate these objects into different classes, anomalies are usually separated by doing less partitions in this space. So the first ones to isolate when you're trying to classify your objects are the ones for which you need less partitions of the space. So if you see here, you can see that this can be considered an anomaly precisely because you only needed this partition to actually isolate this object. So what we're trying to do in a random forest is try to isolate an object. So basically, if a particular decision in your decision tree immediately isolates an object from any other branches, then that object that was so easy to isolate must have particularly different features than the other objects because it just took one cut to isolate it. So anomaly detection based on isolation trees is a very effective way to find anomalies in large data sets. And in fact, it's been widely used in anomaly detection in astronomy. And of course, you can do this many times using not only one decision tree, but many of them, and construct a score by looking at typically how many branches or how quickly you isolate that particular object when you use different features. And you can assign an average score by looking at the number of partitions you need to isolate that object in the different decision trees to provide a final anomaly score. So if you are interested in methods of anomaly detection, then random forest can be a good tool to do that, but there are, of course, many other ways to do that. Okay, so this is what I had for today's lecture, and I wanted to give you with a final thought regarding exploration of data in astrophysics. I think you've by now realized that we're rapidly moving towards a very rapidly increasing data intensive way of doing research. We're getting extremely large amounts of data coming our way, and the exploration of those data sets is a central theme in astrophysics today. And probability and statistics are obviously the necessary tool to do that. So there's no way you can do data intensive astronomy if you don't understand the basics of probability and statistics. And I hope these lectures have been useful in you trying to get those basic notions. And one other thing that I want to point out here is, of course, there's been a lot of interest in archival science and archival research in astrophysics over the last years. And the reason is because these methods of statistics and machine learning are making possible the exploration of extremely large data sets. And a lot of those large data sets are already there. It's not that we need new telescopes like JWST or LSST to actually do research. There's a lot of archival research possible with existing data sets. And one of them, of course, you've been trying to get familiar with this week is the Chandra Source Catalog. So the Chandra Source Catalog, but also every single survey that makes observations public is in principle a mine for discoveries. And I encourage you, especially given the fact that maybe your observational resources are limited, to do research with data. And anything that you can learn about data mining, etc., that's exactly the kind of research that you can do these days very easily with these methods. So I hope that was enjoyable, and I wanted to leave you with a little summary of what we explored this week. And so on the 5 different lectures, and I just wanted to leave you with one central idea of each of these lectures. The first one, lecture 1, we basically saw that X-rays open up a window to the most energetic phenomena in the universe. We saw how they help us explore supermassive black holes, the explosions, the most intense explosions resulting for the collisions of neutron stars, etc. But X-ray astronomy also represents a statistical challenge, because we collect very few photons in our observations, and we need to infer the physics from very few photons, and statistics and probability is exactly what allows us to do that. In lecture 2, we learned about 2 different interpretations of probability: the frequentist interpretation to probability and the Bayesian interpretation of probability. And we learned how basically for the frequentist, the probability of something happening is related to the frequency of how actually that happens in a number of experiments, and they interpret the model parameters as fixed quantities. And the Bayesians, on the other hand, interpret probabilities in terms of the degree of belief, how much you believe that parameters have a particular model given your data. So the other way around, by associating those models with random variables. In lecture 3, we learned about fitting models to data. We learned that models are not reality; they are just our best shot at trying to make sense of reality. And we saw how statistics, and in particular Bayesian statistics and the Bayesian evidence, allow us to compare models that attempt to explain the same set of evidence. And statistical methods like MCMC allow us to characterize complicated posterior. So we introduced the concept of Mcmc sampling to explore posterior distributions that are very complicated, and we applied that to a couple of specific problems in X-ray astrophysics. And in yesterday's lecture, we talked about the variable universe and how that is opening a new window of discovery. We also saw how in X-rays, variability is very difficult to evaluate for the same reason I mentioned before, because we only deal with a few photons in most of the cases. But statistical methods based on a model comparison and likelihood ratios are our best tool to deal with inferring variability from limited data sets. And today we learned about astronomical data sets, how big they've become, and how machine learning is helping astronomers to deal in the best way to sort that information into actual physical information, for example, in the case of identifying time domain objects that are of particular scientific interest. So that's where I want to end today. I hope this has been informative. Of course, there's a lot more to say about machine learning, and I just wanted to give you a initial summary as to different types of methods. But there's many more things to say about that, and hopefully we'll have another opportunity to go more into detail. And of course, I hope you've enjoyed also last week's lectures on astrochemistry. And please feel free to reach to any of us who spoke during these 2 weeks with questions or potential projects that you'd like to work on.
All right, thank you, Juan Rafael, for this lecture. I'd like first to remind everyone that all the lectures from this school, including, of course, Juan Rafael's lectures that he just gave us a nice summary of, there that you can find them at any time. You can find the recordings in our YouTube channel. So in case you need to go back and just take a look at a specific point in time of the lectures, you can do that at any point. Okay, so in general, I'd like to, of course, thank Juan Rafael because he has been instrumental in organizing this school throughout the years, and in particular this year he took it upon himself to give us a very thorough series of lectures on his closest field of expertise and work. So we are, of course, very appreciative of that. And I hope that all the students that attended the school, and of course our students at Universidad de Antioquia, will appreciate very much that it's a very, very rare opportunity that we have here to work with the person who works closest with Chandra data, with X-ray data, with analysis of X-ray data, and of course machine learning and statistics. So of course we'll also be in touch with Juan Rafael for any further research ideas that the students may have or they may want to participate in. So just so everyone attending keep that in mind. So thank you, Juan Rafael, of course, for all these years and for this year as well in particular.
Well, thanks, Herman, and I hope this really helps filling some gaps. I mean, the spirit of this school has always been for students at Universidad de Antioquia, but also elsewhere to, get some additional expertise from experts who might not be in Medellin or in Colombia. And of course, I hope this year has not been the exception. We had to do it remotely. We hope we'll see how things go, but we hope that next year we'll come back to some in-person classes. And of course, just to re-emphasize what you said earlier, there's plenty of projects, there's plenty of discoveries to be made with data, with astronomical data. I definitely encourage you at Astronomy UDA to actually profit from every single data set that you have and from these methods that we've been learning through the week to do science. Because, speaking only about the Chandra source catalog, I mean, I have to say this again, most of the sources in that catalog have never been studied in detail. And if you have interest in high energy astrophysics, black holes, etc., please reach out, and I'm sure that we can come up with interesting projects to do using Chandra or XMM or other types of data sets. That said, I thank you guys for organizing the online sessions these 2 weeks, and I certainly hope to see you again in 2022.
We certainly hope so. I'd also like to thank our speakers for the first week for the astrochemistry part of the school. Edgar Mendoza, Nienke van der Marel, Gustavo Cruz Diaz, Koyu Chuang, We'd like to thank all of you for also being a very important part of the school. We know our students have asked us for years to include the subject of astrochemistry anywhere in the undergraduate program. We only attempted to show a few of the things that you can do in astrochemistry, but that's certainly also a very current and hot subject of study in astronomy that we hope will also inspire some students to work in it. Okay, I think that's good for now. Again, thank everyone who was involved in organizing the school, the speakers, the other organizers, the students from both UDEA and elsewhere in around the country and the world. Thank you for staying through to the end, and I hope to see you soon. Again, there's one final announcement that I'd like to make. We're also organizing. Well, but this. I should probably do this in Spanish, but I'll do this in English just so everyone can understand me. We're organizing a school for I think it's the second week. Yeah, the second week of February next year, around the subject of Gaia and stellar cartography that we can do with Gaia-related observatories and archival data. It will be entirely in Spanish, so just a heads up to anyone who might be interested in participating. We'll also do a streaming like this, like we're doing it right now. Do an in-person experience. We'll give you more details as the details get more figured out. But please stay tuned through our social network channels. I think mostly Twitter. So Twitter, Astronomía UDEA. Please follow us, and you'll be able to know the latest news about this school and other types of activities that we're doing. Okay, so I think that's it. Thank you, everyone, and we'll see you hopefully soon. Goodbye.
Bye-bye.